This video is going to demonstrate how we can connect the procedures for finding equivalent fractions to the representations here. So think about a set of equivalent fractions. Maybe you're thinking 2/3 is the same as 8/12, right? I mean, you can come up with any pair, anything that you'd like, but let's start with that pair for now. Now, first we'll start with the area model, or actually, first we can even start with the set model. And what I want us to see with the set model is the set model first just start with any with either of the two fractions and think about, okay, to show 2/3, I just need a set of 3, and then I can color 2 out of the 3 or change something, right? So it's 2 out of the 3, and that is the set model. In this case, we just want 2 somethings out of the total, right? 3 here in the denominator means my set is made up of, or my whole is made up into 3 equal parts. And so with the set, then they're just each piece is exactly the same. So I just need 3 of them in this case. However, I want to show that 2/3 is the same as, right, is equal to 8/12. So if I see this is my 2/3, and we can even color in, right, 2 of them. What we want to see though is I don't have 8 or 12 of anything here. But what I can do is make this set bigger. And by creating this bigger set, it is now going to change the way we define the whole. So what we want to see is not one whole of 3 pieces, but one whole of 12 pieces. So here, this is my one whole. And now if I was able to copy and paste, right, then we would see that these would still all be colored in if I copied and pasted that first row. And now what we can see is that each column, right, before I had 1/3 here and 1/3 here. And now as I look down the whole in the whole set, I still have this is a third and this is a third. And so I can see my 2/3 right here is 2/3. And we can see that that is, sorry about that, erased too much. I didn't want that. That is literally 1 piece, 2 piece, 3 pieces, 4 pieces, 5 pieces, 6 pieces, 7 pieces, 8 pieces, right? 8 is the same as 8/12. So that's how we want to show this equivalence, that it's literally exactly the same. And that's what the equal sign means. But now let's talk about the procedure of going from 2/3 to 8/12. Many of us think about it as times the numerator, right? Times 4 times 4. Mathematically, a more accurate way to write this would be this notion of 4/4. Because what this simplifies to, right? This is our multiplicative identity. This is just the number 1, right? 4 divided by 4 is just 1. And so now let's think about what did we do to this 2/3? How do we see it being multiplied by 4? One way we can think about it is we had one row of 2/3, and then to get it, we basically, you can think about it like we scaled it up. So that when we took this 2/3 and we had it 1 time, 2 times, 3 times, 4 times. And so we had the entire denominator, right? The 3 4 times, and the numerator 4 times. And thus by scaling, right? Think of this idea of multiplying by 4/4, scaling up this set of 3 circles to begin with to this whole set of 12, right? We still have this relationship of 2/3 of this whole, or before, if it was just these 3, when it was just these 3 circles, right? We had 2/3 of that whole, but now we scaled it up. And so we created 4 times the green ones, right? We have now 8 green ones, and then 4 times the whole, which is now 12. All right, so that's the set model. Can we connect this to the area model? And first, we're just going to start with the circle. And so let's at least show how they're equivalent. So first we have this space, and we can color it in. Let's use green again. So we're going to do 2/3. We can even turn on the labels if you want to see, verify that. But now let's create another one, and we want to show 12ths. And right here, this is the one way we can see here, they're the exact same size whole. And now check it out. How many 12ths, 1, 2, 3, 4, 5, 6, 7, 8, do we need to color in? So that way they're the exact same area, right? The same amount of space that is being taken up. And that's how we can show equivalence here. Now, again, the question is, well, how do we connect this model? I wanted to put the 2/3 on top so it was a little bit darker, so we can pay attention to some key pieces, like right here. I'm going to highlight that in yellow. So now again, think about how can you explain this 2/3 being multiplied by 4, or 4/4, either the numerator and then the denominator, or this idea of 4/4, right? Or think about it similar to this notion of scaling. What did we do to these 2/3 here to create 12ths, or even each individual third? And one thing I want you to notice, I'm going to erase these and we'll just look at 1/3 for now, is this idea, right? I see similar to the set model, similar to over here, right? 1/12, another 12th, another 12th, another 12th, right? We see that each third, right? This whole thing is 1/3, and then keep going is 2/3, right? This yellow piece that I first colored in, hold on, I'm trying to erase these guys so that we can highlight the yellow outline, right? This 1/3 here is now cut into these 4 equal pieces. So think about that. I'm taking one, or think about the whole, right, being cut into, each third being cut into 4 equal pieces. And that cutting up into those 4 equal pieces is happening to both the numerator, right, the parts that we have, the green here, and the denominator, the total number of parts in the whole. And so that's why it's like this idea of scaling up, where we're not changing the fraction, right? We're multiplying by the multiplicative identity, but we are changing the size of the pieces and how many we have. So, right, the numerator tells us, right, how many pieces we have, and the denominator tells us the size of the pieces. So, right, we're changing the size of the pieces and how many pieces we have, but we're keeping this relationship so that we still have that same amount of space, in this case with the area model, or same amount of relation, right? The scaling up, the same relationship where we're using 2 out of the 3 total columns here. So this is why the fractions are equivalent. We haven't changed the quantity, right? We're keeping them, we're multiplying just by 1. We're not changing the quantity, but we're changing the size of the pieces, and to keep this, and then, right, how the total number of pieces that we have, right? We went from 2 total pieces to 8 total pieces when we're talking about equivalence here. lastly, we can do see the exact same ideas in our length model. And we want to show, and so exactly like how we did the area model, we want to see that 2/3 is the same as 1, 2, 3, 4, 5, 6, 7, 8 twelfths. And whether you put them on top of each other, like this, or next to each other like this, right? We're still comparing the length of each. And so now again, how can you explain, right, how these 2/3 are now kind of cut up each into these 4, right? Each piece here is cut up into 4 more pieces, right? And we see that here, or even here, right? We're taking the 2 and cutting up into 4 more pieces, 4 equal pieces, and taking the 3, the whole, right? Cutting up each piece into these 4 extra pieces, so that way we're keeping the same scale of 2/3 of the whole, which is the same as, right, 8/12 in this case, when we had changed the number of pieces in the whole to be 12.